You all see my screen? Can everyone see my screen and hear me? Okay, perfect.
Yep.
So, hi, I'm Ariadna Murgia-Berthier. I'm a grad student at UCSC, and I'll be talking also about nuclear equations of state and how do we implement the neutrinos in HARM. So let me begin by motivating it a little bit and start my video too. So why do we actually need neutrinos for this part of the handoff, which is the post-merger? So as the two neutron stars orbit each other, at the very end, we're going to have a black hole surrounded by an accretion disk. This accretion disk will have high temperatures and high density, such that the photons are actually going to be trapped and be super Eddington, creating this very thick disk in the outer regions of the disk. But as we go inside, first of all, we're going to have, as Luke said, this recombination area where from alpha particles you get free nucleons. And as we go inside, there are going to be beta processes like this one that are going to create neutrinos. The neutrinos have very, very low cross-section, therefore can just escape from the disk and cool it off and make it way thinner. So as we go inside, first we have a region that's transparent to neutrinos. And then at some point, we actually will have that the optical depth is going to become larger than 1, and it's going to be opaque to both neutrinos and antineutrinos. And at some point even, we're going to have that the neutrinos are going to be trapped, just as the photons, but that's very inside in the accretion disk. Here I'm showing all the neutrino reactions that we expect to happen in the accretion disk. So first of all, we have the charged beta process. We also have the plasmon decay, electron-positron pair annihilation, and as an opacity source, we're going to have the absorption, which is just the inverse reaction of the charged beta process. Notice that as we have very neutron-rich material, this reaction is going to be the one that's dominant because this reaction is the one that has the most neutrons. And therefore, we're going to have lots of antineutrinos being created. But on the other hand, as the opacity source, in the neutron-rich material, this is the reaction that's going to be dominant. Therefore, the neutrinos are going to have a higher opacity. And in fact, if you notice, right here in the disk, you first become opaque to neutrinos and then to antineutrinos, which just follows from these reactions right here. Now here I'm just showing a plot on the mass accretion rate of the accretion disk as a function of radius and what happens at certain radius. So as you saw from before, in the outer regions, we're going to have lots of alpha particles. The photons are going to be trapped. And then at some point, we're going to have free nucleons. And then the neutrinos are going to start to be created, and we're going to be cooled by neutrinos, making the disk very thin. And at some point, we're going to become opaque to neutrinos and antineutrinos. If the mass accretion rate is high enough, we're going to be trapped, but we're not going to consider those cases. So then again, let me just go back as the question, why do we need neutrinos and why do we need to model this as realistic as we can? First of all, we have this part right here where you have the recombination, and that requires a realistic equation of state in order to consider that energy given by the recombination. And then in here, when we have that the neutrinos are being formed and then become opaque, we're going to have to need some kind of transport scheme or leakage scheme to actually accurately represent the neutrinos escaping and the effects that they have on the electron fraction and on the temperature too. So these simulations have been done by lots of groups, as Scott just talked about. And the main problem is that, as Luke was saying, there's this transition electron fraction where you can either create lanthanides or don't create lanthanides. And the nucleosynthesis in accretion disk is around that electron fraction. So the final composition is still very uncertain. Different groups get different electron fractions. So we need to try to be as realistic as possible so as to try to get the best electron fraction that we can for the nucleosynthesis that we need. So we absolutely need to accurately represent the neutrino physics in the accretion disk in order to get the nucleosynthesis as best as we can. So that's why we need to implement realistic neutrino physics in GRMHD code as HARM. So those were our objectives. So this is a working group 2, and as Scott already said, we have two main objectives. So first, we want to implement a realistic equation of state in HARM 3D, which will take tables from stellar collapse and will do an interpolation of the tables so that HARM 3D is completely agnostic to the equation of state. And this will naturally take care of alpha particles and also the neutrino pressure terms. And additionally, we want to add a neutrino leakage scheme that will take care of the heating rate and the cooling, well, the heating and cooling rate, and also the change in the electron fraction. That's going to be very significant and very important. So the neutrino leakage scheme is key. So in the neutrino leakage scheme, we're going to calculate the opacity, but it's going to be the spectrally averaged opacity. So we are not considering all kinds of spectra. We also calculate the optical depth. And what we're going to do, as Scott mentioned, is we're going to add these source terms into the equation, into the energy and number equation. So let me give an overview on where we actually put the EOS. So the interpolation that we do from the EOS comes from this really nice driver by Evan and Schneider, and it's actually based on Dan's really cool paper. And this is all in the stellarcollapse.org webpage, just so you know. And we needed to add it in 3 places. So first of all, we needed to add it in the routine that does the conserved to primitive variable solver. We also needed to put it in the calculation of the sound speed, because that comes into the calculation of the characteristic velocity. And the third place where we needed to put the equation of state is in the primitive variable energy, because we needed to add the temperature as a primitive variable. So the energy is going to now be a function of the density, the temperature, and the electron fraction. So these two were relatively simple. It's just a call to the EOS interpolator. And I'm going to spend a little bit more time explaining what we did for the routines that go from the conserved to primitive variables. So as Scott was already saying, we actually have implemented now 4 routines that do the conversion from primitive variables, from conserved variables to primitive variables. So the method that was already implemented in HARM 3D was this really cool method by Scott, and it's a 2D method. In here, we have 2 equations that we need to solve, which are just based on the GRMHD equations. You can reduce them to 2 equations, where we have 2 independent variables, which are the velocity, and this W, which I'm defining right here, it's very related to the enthalpy. Now we have 2 equations, 2 independent variables, so we can solve the system. And here, right here, I am circling all the variables where we need to do an equation of state call, because the enthalpy is going to depend on the pressure, and also the pressure. We're going to need to have the pressure as a function of the density, the electron fraction, and the temperature. And that is exactly what the interpolator does. It gets the pressure and every other variable as a function of the density, the electron fraction, and the temperature. So with that, we already did this routine, and we added 3 other more just to make it as robust as we can possibly do, and as accurate. So the second routine that we added was this 2D method, but instead of the guesses that we had, we added some safe guesses that come from this paper by Cerda-Duran. And in this case, we implement a really, really high Lorentz factor as our initial guess. And we also have the enthalpy guess with the maximum pressure from the table. This safe guess has been noted to add robustness to the calculation of the conserved to variable solver. Now, the third routine that we added was again a 2D method, but instead of doing a Newton-Raphson, we implemented a dogleg method, and you can check that in the numerical recipes book. So the nice thing about the dogleg method is that it allows for a more robust convergence, because you can have an initial guess that's not quite the solution, and you can get more robustness. Whereas in the 2D method, you need to be very, very near the solution. The guess needs to be very, very near the solution in order to converge. So these 2 methods were to add robustness to the 2D method. And additionally, we added another 4 routine, which is also based on a routine that Dan has, and that's in the Cerda-Duran paper. And in here, instead of a 2D method, we actually have a three equation method. So the equations to solve are, these two are the exact same questions than in the 2D method, but instead of getting the velocity as the independent variable, we have the Lorentz factor as the independent variable. And additionally, we have this third equation right here, which is just that the energy needs to be equal to the energy given by the table. And again, this is where the calls to the equation of state happen. We need to get the energy as a function of the density, the electron fraction, and the temperature, and also this enthalpy right here. Now, what we can do next is test those EOS interpolations. And what we can do is we took a grid of temperature and density, and we constructed primitive variables from the temperature and the density for a certain Lorentz factor and for a certain pressure over magnetic pressure. And with that, we can construct our grid. We can then go from primitives to conserved variables in an analytical way and use our routines to go from the conserved variables to the primitive variables to recover them and try to see the error between the original primitive variables and the recovered primitive variables. And this is what we're showing right here. This is the relative error in the sum of all the errors in all the primitive variables. And this is actually a plot that Scott showed, but this is with all the different routines that we have. So this is this is for the 2D method. This is for the 2D safe guess. This is for the dogleg method, and this is for the 3D method. So as you can see from here, the 3D method is the most accurate of the methods, but it's also the least robust. So what we did then is that the 3D routine is our primary routine. And if that one fails, then you try the other three routines. So these are going to be the three backup routines that we're going to be using so that our results are as robust as we possibly can. And again, this is all based on Dan's paper, and the driver is from the stellar collapse papers, which I highly recommend you check. So let me talk then a little bit. So what we can conclude from this is that we do a pretty good job in getting the primitive variables, which is really nice. So at least that part of harm is already agnosticized to the equation of state, and also the characteristic velocity. And is there a question? Okay. And so basically we have already agnosticized harm to the equation of state. So let me talk a little bit about some subtleties with the EOS that we have found. And the subtleties occur in the atmosphere. So what we did to test the equation of state was an isentropic Fishbone Moncrief disk. So we took the enthalpy from the Fishbone Moncrief paper, and we said, okay, let's just do it as isentropic. So the disk is isentropic, and it has the enthalpy from the Fishbone Moncrief disk. And here I'm going to show two different movies to show the different subtleties that we found. So we first said, okay, let's try to make the atmosphere with the same entropy as the disk and an enthalpy equal to 1, which is what's used in the Fishbone Moncrief for the atmosphere. You haven't, sorry? So you have an atmosphere where the enthalpy is 1. And what's going to happen here is, if you notice right here, one of the things is that the central density compared to the atmospheric density, it's only an order of magnitude in difference. So I'm going to show you the movie of what happens, but you're going to see an outflow begin from the black hole onto the torus. That is a really common thing in all the disks that we have. That even happens in the gamma-low equation of state. But in this case, this outflow is going to be so energetic that's going to obliterate the disk. So let me show you what happens. So as you can see, the outflow is very, very dense, and it has really high temperature. So it just obliterates the disk, which is something that we don't want to happen. And this is just due to the fact that the gradient, that the density in the central regions and in the atmosphere, the gradient is really low. So it's only an order of magnitude difference. We want it to have lots of orders of magnitude difference. So then what we did is, okay, let's try to have the atmosphere with higher entropy than the disk, but still with an enthalpy of 1, because if we have the enthalpy and we have the entropy, we have all the other variables. So let me show you what happens in that case. And you're going to see that the outflow, in this case, it's not that dense, so it actually does not do anything to the disk, but you start to see a lot of diffusion in the outer regions of the disk. So this was actually something that I wanted to discuss yesterday. And luckily, in one of the breakout rooms, we got to discuss these two different cases and some suggestions on what to do. And we actually came up with something. And Scott, you're going to like this. I'm really glad that you're here. So what we found is that in the tables, the minimum enthalpy is not 1. So usually for the Fishbone Moncrief disk, for the outer regions, what you need is that it's that in the limit when the pressure goes to 0, which is a limit that the outer edges must have so that you are in hydrostatic equilibrium, then the enthalpy, well, the internal energy has to go to 1 in code units. But the table, as Scott already mentioned, has a negative energy density in some regions, which are actually right here, the energy density is negative. So the enthalpy will not go to 1, it will go to something a little bit lower than 1. So there is a minimum enthalpy that's not 1 in the tables, and it's like 0.990 something. So it's really close to 1, but not quite 1. So then what we did is, instead of defining the disk to where the enthalpy is equal to 1, we defined the disk as where the enthalpy is very similar to the minimum enthalpy in the disk, in the tables. So that actually helps a lot with the problem, because as you can see, the central density compared to the atmospheric density is different by orders of magnitude. And just let me show you what happens. So you start to see an outflow again, but the outflow is not powerful enough, and you actually don't see that much diffusion. There's still a little bit of diffusion, but it is not as bad as the other cases. And we're very consistent in the sense that this enthalpy, we know that it's the minimum density in the tables. So I think that this is the path to the solution, and it was a great breakout room session than yesterday, because I think that this is the way to go. So this was all with the equation of state, and only equation of state, but let me go into the leakage scheme, because that is where we're actually more interested in the fact that we're going to change the electron fraction with the leakage scheme. If we only use the equation of state, we're going to take care of the neutrino pressure and the recombination energy, but the electron fraction is just a passive scalar. We need to do more in order to get what electron fraction is the most realistic one. So in this leakage scheme, these are all the reactions that we considered, and this is all based on these really nice papers by Rufford et al., Galeazzi et al., and lots of other papers. So in here, what we're going to, including actually Dan and Brian's paper, and in here we're going to consider the charge beta process, the electron-positron pair annihilation, and plasmon decay, and those are all going to alter the electron fraction greatly. And as our opacity source, we're going to consider this absorption right here, which again is the inverse of the charge beta process, and also scattering with free nucleons. So as Scott already mentioned a bit, in the leakage scheme, what we do is we add source term to the equations. So in here, we add this heating or cooling rate Q to the energy equation, and we add this absorption and emission rate to the electron fraction equation. Usually this would be 0, and that would be a passive scalar, which is something we don't want for these cases. And what's really nice for the leakage scheme is that the effective rates are an interpolation between the optically thin and optically thick regime. So in here, I'm showing what the effective rate is, and it is just, and here, this is the diffusion timescale and the emission timescale. And what's really nice is that if we are in the opaque region, then the effective heating and the effective heating and emission rate are going to just go to what should be if diffusion were only happening, which would be in the opaque region. Whereas in the transparent region, we're going to have that the emission rate is going to be the sum of the emission rate from all the reactions that I showed. So the beta process, the plasmon decay, and the pair annihilation. And this is the same for the heating rate. And again, the opacities that we're going to use are the scattering with free nucleons and the absorption opacities. So in the very end, what we're going to alter are it's the right-hand side of the equations, and that's going to help us get the more realistic electron fraction. Now, what we can do to test the leakage scheme, and this is actually really nice work by the Los Alamos group, is that we can take an isotropic, optically thin, constant density gas, just a couple of cells that have constant density, constant temperature, and just let them evolve. If we do that, then our equations just reduce to these simple equations where Q and R can be semi-analytically calculated, because you still absolutely need to do some table interpolations because you need the chemical potential. But you can semi-analytically calculate Q and R, and then with that, you can also just evolve this equation. So what I'm showing here is the temperature as a function of time, and time is in seconds, and the electron fraction also as a function of time. The pink one is the semi-analytical calculation for Q and R, so it's just semi-analytically evolving these equations. And the blue part is what the simulation gives me as the temperature and as the electron fraction for, again, an isotropic, optically thin, constant density gas. And what I want you to, this is for the electron antineutrino and only considering the beta process, but we of course have also tested all the other processes and you see something similar. And what I want you to notice is that we are in agreement. So we actually do a good job of getting the Q and R, at least in the optically thin regimes, because this is only testing the optically thin regime. Now let me talk a little bit about how we calculate the optical depth, because this is something that's really interesting. So the optical depth is needed to calculate the diffusion timescale. And we follow the prescriptions in this paper by Nielsen et al. And Dan and Brian. So in here, we are going to turn a global calculation into a local calculation where we center in one cell. And then we say, okay, so what's the minimum kappa ds to each of the neighbors? And we're going to do an iteration over that. So this is basically the kappa ds, which is just a delta tau, a delta optical depth. And we're going to get the minimum of the optical depth to the neighbor plus this delta tau. What this is going to be doing is you're going to say to the neutrino, what is the path of least resistance? So as you do more iterations, you actually go larger in the domain. And you're going to tell the neutrino what's the path that the neutrino should choose so that it's the least, with the least resistance. So it's a really nice calculation because even though it's a local calculation, you're actually doing a global kind of calculation. And what we did is we tested this with a sphere. So the sphere just has the constant density inside and constant density outside, also constant temperature and constant everything inside and outside. Because we can analytically calculate the opacities there, so we can then analytically calculate the optical depth there and compare to our calculation from the optical depth. So one of the things that we noticed is the importance of the iterations, because if we do only one iteration, you're going to only tell the neutrino which of the neighbors at that point is the path of least resistance, but you're only going to tell one of the neighbors, but you actually want to go farther and farther in the domain, and as you iterate, you go farther and farther. And with that, you're going to tell the neutrino its entire path of least resistance. So in this plot right here, I'm showing the importance of how many iterations you do. So the pink, this is the optical depth as a function of radius. This is the optical depth to neutrinos nu e. And this is also for the emission rate, because we actually need to calculate 12 optical depths, 2 per neutrino species, because we have the heating and the emission of optical depth. So we have 3 neutrinos, 3 antineutrinos, 2 times per neutrino, so 12 optical depths. So I'm just showing one. This pink plot right here is the analytical calculation just by using this equation right here with the opacities for a sphere of constant density and constant temperature. And the different lines represent, in our simulation, we did just one iteration or 5 or 10, etc. And what you can see is that if we only do one iteration, we actually do a pretty bad job. So if we start here, it's only going to tell the neutrino to go to one of its neighbors, and the optical depth is not going to be as nice. But as we increase iterations, we start to get to the analytical curve. So we need a convergence criterion. We need to make lots of iterations and then have a convergence criterion as to when we stop doing the iterations. And we have a convergence criterion, and with that, this is what we get. So this is the simulation, and this is the analytical curve. So we do a pretty good job of getting the optical depth. And our convergence criterion basically is based on, we calculate the opacity at the optical depth, and then we calculate the optical depth again, and we see the difference between these two optical depths. And we say, okay, when this difference is less than an epsilon, it's converged. And also we set a constraint on the first derivative. So we actually do a really nice work on the optical depth. And so with that, we already have tested the leakage scheme, and we have already tested the optical depth. So with that, our conclusion is that we're ready to work with the tabulated equation of state and the leakage scheme ready. But we absolutely need to understand, so the future work would be to understand more the initial conditions, particularly in the atmosphere. We're still working on that a little bit. And Scott mentioned that there is a very robust routine that goes from conserved to primitive variables that we're very interested in implementing, because still with these 4 routines, there are some pesky points, particularly near the black hole, where you have very high velocity, low density, and low temperature, where you're still not converging. It's not that common to not converge, but still there are non-convergences, and supposedly that routine is always converges, so we're very interested in doing that. And of course, the future work, which is the actual goal, is to use Skynet to do the nucleosynthesis now that we will have a realistic electron fraction. And with the handoff, we're going to also have realistic initial conditions, or as realistic as we can get. And I just want to say thank you. And if you have any questions, feel free to ask, I guess, at the break. But thank you very much. And this has been really, really fun to do. Programming is really fun.
All right, thank you so much, Ari. Do I see any hands up? Scott's clapping. So I had a question about the calculating the optical depth to escaping. When you talk about the iterations, is that like you have to go cell by cell, and for each cell you have to do those certain number of iterations?
Yep.
So does it help to kind of start with a guess? And if so, can you kind of guess based on the neighboring cell, and then kind of when you move to the next cell, you take it from there?
So I don't know. I mean, I guess a guess could help, because we start with optical depths of 0, and then we do the first iteration, and I mean, lots of iterations. I don't know if it will be good to start with a guess. It might, because so for sure at the plots that I show for the iterations are at the initialization, because once the initialization happens, you only need 1 or 2 iterations to converge always. So it's actually just that very first. So I think that actually that might answer it. So that would be the guess, I guess, because it's only slow at the very beginning. Well, slower at the very beginning, and then it just you need 1 or 2, 3 at most.
Oh, okay. That's good, because I was getting nervous when I saw like 1,000 iterations per cell.
That's I should clarify. That's at the beginning.
Okay. And David Radici has his hand up.
Yeah, I have a brief comment about this, since we use the same schema. What we do in our BNS simulations is exactly that. So we first compute the optical depth using one of the standard algorithms out there, using ray by ray, for example. And then we use that as initial guess. And then apart from this initial time, we just update the optical depth using the algorithm.
What, can you repeat the name, please, so that I can write it down?
So we basically just compute the optical depth by integrating ray by ray.
Okay, yeah. Okay, the ray by ray.
And that's our initial guess. And starting from that time, we don't do anything special anymore.
Okay.
Thank you.
Thank you.
I'll look into that.
So it's 12:12. Maya suggests that we break off because we only have limited time before the next discussion session starting at 1.
So Manuel, I was going to recommend actually taking a full hour for a break. I know personally I could use it to take care of a bunch of stuff. And in the last 2 days, the 1 to 2 session where we kind of do the pre-breakout discussions, those have all actually run pretty short, and then people have seem to be more eager to get into the breakout sessions themselves. So
yeah, I
would
think
propose
we can do that, but I think not everybody is right now on the call. You know, you can do that.
I think there's a much bigger risk of starting a session early to miss people.
So why don't we? I think send an email to the workshop starting at 1:30 if you tell all the participants, because not everybody is here today.
Okay, and the breakout session. Sorry, what's listed as the brief discussion on key questions. That's going to be on this same Zoom channel. Is that right?
That is correct. Everything, the information is all on the Google Doc. So this is in the pre-discussion is on the main Zoom channel. And if you want to start at 1:30, just make sure that all the participants are told, because they may not know. Not everybody is attending today. So send an email to workshop announcing that it starts at 1:30, but the rest, everything stay the same. So it means that the discussion, you know, the gathering of the questions before the